You know, every time you use your phone, or you see an AI generate some amazing image, or even when you're just driving an electric car, you're basically commanding this invisible army, an army of billions and billions of tiny particles. And figuring out how to control them? Well, that's the secret to pretty much all of our modern technology. So today, we're going to pull back the curtain on how it all really works, from the electrons to the chips to the secret ingredient, the rare earth elements that make it all possible.
So it all starts right here, with the electron. We're talking about countless little particles, all just buzzing with energy, creating the flow of electricity that powers, well, everything. This sheer scale is it's almost impossible to wrap your head around. But all that raw, chaotic energy is just the starting point.
Because, let's be honest, a chaotic flood of electrons isn't really useful on its own, is it? We need to bring some order to that chaos. And the tool we use for that job is the semiconductor. Think of it like a traffic cop for this crazy electron superhighway. It's what teams all that chaos into something we can actually direct and use.
And here's the twist. To get the unbelievable speed and efficiency that modern life demands, especially for something as intense as AI, we need a little something extra. A secret ingredient, you could say. And that's where rare earth elements come in. They're like a performance booster, taking our control to a whole new level.
All right, let's build this whole picture from the ground up, shall we? To really get how we control these particles, we first need to understand how they move, or in some cases, how they don't move through different kinds of materials. Let's stick with that highway analogy for a second. In some materials, which we call conductors, think of something like copper wire. Electrons can just move freely. It's a wide-open, multi-lane highway with absolutely no speed limit. But then you have other materials, called insulators, like the rubber around that wire, where the electrons are locked down tight. That road is completely blocked. No traffic is getting through, period.
And then you have the semiconductor. This is the absolute game changer. It's not always a highway, and it's not always a blocked road. Instead, think of it like a road with a whole system of smart traffic lights. We can tell the electrons exactly when to go and when to stop. And that gives us precise, programmable control. This right here is the key to everything.
So, how do we actually operate these smart traffic lights, right? What's the thing that flips the switch from red to green? Well, like a lot of things in the universe, it all comes down to one thing: energy.
So, inside a semiconductor, electrons are just kind of hanging out in this low-energy state we call the valence band. You can imagine them stuck down in a valley. Now, to get moving and actually create electricity, they need a little boost of energy to jump over a hill, a barrier we call the band gap, and get to the conduction band on the other side. Once they make that jump, boom, they're free to flow and create a current.
Now, making that jump efficiently is absolutely critical. For the kind of high-speed calculations you need in AI, you can't afford any delays or errors. So this is our first real hint at why those rare earth elements are so incredibly important. They basically act like guides, building a more stable bridge over that energy gap. This makes the jump quicker, way more reliable, and it cuts down on the chances of electrons just leaking away as wasted energy.
You see, a pure semiconductor like silicon is a fantastic starting point, but we can make it so much better. We can essentially hack the material using a process called doping. And that just means we intentionally add these tiny, targeted impurities, just a few special atoms here and there, to totally change its electrical properties.
So, the first way we can do this is called N-type doping. The N stands for negative, which makes it easy to remember. We add impurities that have extra electrons that they're totally willing to share. This creates a surplus of these negative charge carriers. It's just like adding way more cars to the highway, all revved up and ready to move the second we give them the green light.
The other method is P-type doping. And you guessed it, P stands for positive. In this case, we add impurities that are actually missing electrons. This creates what we call holes. Now think of these holes as empty parking spots. The nearby electrons will naturally just jump into these empty spots, and that movement of electrons, hopping from hole to hole, also creates a current. So we've got two different methods, one with extra electrons and one with extra spaces, but they both get us to the same goal: much, much better electron flow.
Now, here's where it gets really clever. When we combine these two different types of doped materials, our N-type and our P-type, we can create the fundamental building block of all modern electronics, the digital switch.
Okay, so when we join a piece of P-type material right up against an N-type one, something fascinating happens right at that junction. The extra electrons from the N side and all those holes from the P side, they interact and they create this natural electrical barrier that just stops any current from flowing. But And this is the magic part. If we apply just a little bit of voltage, we can push through that barrier and turn the flow right back on. And there you have it, our very first basic digital switch. It's either on or it's off. The PN junction is the foundation, for sure. But the transistor? The transistor is the masterpiece. A transistor takes that basic junction and it adds a third connection, a gate. This gate acts like a super sophisticated valve. It lets a tiny electrical signal control a much bigger flow of electrons. It's not just a simple on or off, it's a precision instrument. It is the workhorse that powers our entire digital world.
And I mean that literally. The processor that's sitting in your smartphone or your computer, it doesn't have a few of these switches or even a few million. It has billions of them, all packed into a space smaller than your fingernail, all switching on and off billions of times every single second. It's just incredible. So, okay, we've got our switch and we can build billions of them. That's amazing. But to meet the absolutely insane demands of AI and other modern tech, they need to be faster, smaller, and way more energy efficient than ever before. And this is where our secret ingredient, the rare earth elements, comes back into the picture.
And this really is the critical question, isn't it? I mean, we've got our silicon, we've got doping, we've got transistors. It seems like a pretty complete system. So why bother adding these exotic rare earth elements into the mix? What do they actually do that silicon can't on its own?
And here is the answer. Rare earths basically act as a supercharger. Their unique atomic properties create these powerful, super-localized magnetic and electric fields. Think of these fields as invisible guardrails on that electron highway. They guide the electrons with more precision, they reduce that energy leakage as they make the jump over the band gap, and they just improve the overall stability of the whole transistor. And the result of all that? Well, it means those billions of switches can operate faster, more reliably, and with less wasted heat than they ever could with just silicon alone.
So let's zoom all the way back out. We've gone on this journey from a single electron jumping over an energy hill all the way to billions of transistors packed onto a tiny chip. Now let's connect that microscopic world to the massive technologies that it makes possible in our everyday lives. This precise, supercharged control of electrons is exactly what allows an AI chip to perform trillions of calculations every single second. It's what lets the power systems in an electric vehicle manage its battery energy with incredible efficiency. And it's what allows the smartphone in your pocket to run complex apps, process high-res video, and connect you to the entire world, all while just sipping power. And this really is the big takeaway. Without the enhancing properties of these rare earth elements, our technology would just hit a performance ceiling. Our chips wouldn't be as fast, our batteries wouldn't last as long, and our devices just wouldn't be as powerful. Rare earths are the key that shatters that ceiling and unlocks that next level of innovation. So the next time you watch an AI generate an image or you ask your phone a question, just remember this simple chain of command. It all starts with controlling a single electron. That control lets us direct an electrical current, and that carefully directed current is what powers our entire digital world. It's this incredible, invisible foundation, built one supercharged electron at a time.